Okay, so let us continue. And we have now the second lecture by Professor Etingof.
Okay, so let me remind what we did last time. So last time we proved the Grothendieck's theorem. That vector bundles on projective line are of the form O of M1 plus so on plus O of Mn. So of rank n. Where M1, Mn are integers. And so any vector bundle on P1 can be uniquely written in this form for unique numbers M1 through Mn. And I want to start with explaining how this generalizes to an arbitrary connected reductive group. And to do so, I want to reformulate this result in a way that will be easy to extend to any connected reductive group. So recall, so this is the same as GLN bundles. And GLN is the group of invertible n by n matrices. So it contains a maximal torus T, which is diagonal matrices with non-zero entries on the diagonal. And so T is a, let's work over complex numbers. So then this is going to be C star to the n. And what this theorem says is that every, so if I call GLN G, that every G bundle on P1 is associated to a T bundle. Which means that the structure group of this bundle, as people say, reduces to the torus. But moreover, so so what are T bundles? Well, T is a product of C stars, so a T bundle is just a product of C star bundles, and a C star bundle is a line bundle, so it's of the form O of M. But actually, more than that, the same G bundle can come from a bunch of different T bundles. Because when you talk about a T bundle, it actually matters in what order you write these numbers. But for a G bundle, it doesn't. And so, so this means that moreover, if E1 and E2 are T bundles on P1, and well, then they're associated bundles E1 over T with G is isomorphic to E2 over T with G if and only if there exists a permutation sigma in the symmetric group such that E1 is isomorphic to sigma of E2. And so in fact, in this form, this theorem generalizes straightforwardly to arbitrary reductive group. So now, if G is a connected reductive group, So I'm working over algebraically closed field right now. And T is a maximal torus. So then we have the normalizer of this maximal torus inside G. And the Y group is the quotient of the normalizer by the torus itself. Because this group is abelian, it acts on T. And the theorem says that any G bundle on P1 is associated to a T bundle and the same thing is true. And E1 T G is isomorphic to E2 T G if and only if E1 equals to W of E2 for some element of the Y. For GLN, the Y group is the symmetric group, and so it reduces to this state. I'm not going to prove it, but that's what can be done, and proof can be basically reduced to the case of vector bundles by considering representations. So I'm not going to go into that. And so what this says is, so now suppose T is a torus. G. Yes. Okay, so suppose T is a torus. So as I said, torus is isomorphic to C star to the n. But it is so in many different ways because there is an SLN Z acting. And so let me just say a torus without choosing this identification. Then how to classify T bundles on P1. Well, we know T is isomorphic to C star to the n, so this is just an n tuple of integers. So this is in bijection with Z to the n, but non-canonically. What is it canonically? Well, I claim canonically it is something that is called the co-character lattice x lower star of T, which is by definition hom from C star to T. So it's a group homomorphisms. Of course, this is C star to the n, and so this is just Z to the n, but canonically it is this. And it's quite clear why, just by our definition. Remember that such a bundle is defined by a transition map from chart U infinity, which means 0, to chart U0, which means is infinity, G of Z. So in G is a map from C star into our group. But of course, any map like that, well, it's isomorphic to C star to the n. And any map like that has the form Z goes to, well, we discussed for each coordinate, we're going to have a constant times Z to the n. So we're going to have C1 Z to the M1, C2 Z to the M2, Cn Z to the Mn. And these constants are non-zero, and they can be rescaled to be 1. And so in this case, we just get, without these constants, and this is a group homomorphism. So it is a co-character. So this is called the co-character lattice of T. And canonically, our bundles are classified by this co-character lattice. So theorem says that G bundles on P1 are classified by the co-characters of T modulo the Wald group. But of course, this can be so a remark is the co-characters of the maximal torus is the same thing as the characters of the dual torus, which is the same as weights for the dual Langland's dual group. So these are weight lattice let me call it lambda check of the Langland's dual group G check. So a connected reductive group by definition is defined by what is called a root datum. And a root datum is a root system, dual root system, and the weight lattice and the dual weight lattice. So there is a root datum is a thing that has an involution where we can exchange roots and co-roots, weights and co-weights. And that exchanges the group G with the Langland's dual group. So for example, it exchanges SLN with PGLN, and it exchanges symplectic and orthogonal groups, so SP2N and SO to N plus 1. Langland's duality is a deep connection between objects related to G and some objects related to G check. And actually, this is a baby example of a Langland's duality. When bundles, G bundles on P1 are classified by weights for the, so basically by represent, so this X star of T mod W is the same as lambda mod W. So this group G and G check always have the same Wald group. And this is the same as lambda check plus, which is dominant integral weights. Which label irreducible representations. Irreducible finite dimensional representations. So we see that there is a bijection between principal G bundles on P1 and so we have a bijection between principal G bundles on P1 and irreducible representations of the dual group G check. And this is a very baby example of Langland's duality. Of course, it extends much further and much deeper than that. Okay, so this is just one comment. So now we talked last time also about the following object. So X was a smooth irreducible projective curve. Over some field K, and G is a split connected reductive group over K. So in this case, we don't have to assume that K is algebraically closed, but split groups is the same. They are labeled by the same data, namely root system and the weight lattice, and co-root system dual weight lattice. So we have this pair, and to this thing we attached something that I didn't really define in full detail, but at least defined as a functor of points. And this is the stack of bundles, bund G of X. So moduli stack of G bundles on X. So this is a very complicated object. and I explained some of the complications that it comes with. But luckily, many of these complications will not be very important for us. However, I would like to describe this stack as a set a little bit more explicitly. And so this topic is called the double quotient realization of this bond g of x. So just want to make it a little bit more explicit. So for simplicity, let us assume first that G is semi-simple. In this case, we saw that so any bundle by the theorem of Harder that I quoted trivializes once you take out a point. So let's fix a point. So let me first consider the case algebraically closed field. So then we always have a point. And when I write an x, it's really x of k, but I'm going to skip it. And then we have, we can cover x by two charts. So let's draw x. So it's a curve. So if our field is complex, it's a Riemann surface. And then this is our point x. And I'm going to cover it by two charts. So one chart is a disk around this point, and the other chart is the complement of this point. Well, that's if we are working in complex analytic setting, then we can just take a small disk. But in algebraic geometry, we do not have small disks, but we have formal disks. And we can do the same thing by using formal disks. And that we can do over arbitrary field. So the two charts are, first of all, x minus x. This is just the affine curve obtained when you delete this point. And formal disk d sub x around x. But if you are not comfortable with formal disks and you like more complicated things like analytic disks, you can think about them. Okay, so so they do cover our curve, which you can say algebraically as so it makes sense of a range field. And so we can compute bundles by using this cover. If we have only two open sets, we do not have to use a cocycle condition. We just need to fix one transition map. So for this purpose, we need to say what the intersection of these two things are. And you might guess what it is. So if you think about analytic disk, the intersection is, of course, everything except the center of the disk. So this is called the puncture disk. So this is the puncture disk. But again, if this disk is formal, well, it has only one closed point, which is this point, and you deleted it, so it sounds like you get an empty set. Well, you don't get an empty set because you should talk about it in the language of algebraic geometry, which is the language of rings of functions. And so, so functions on the first set, O of x minus x, this is clear. This is just regular functions on this affine curve. X minus x. And I'm going to denote this by r. And then O of dx is functions on the formal disk, which is the following, that if you choose a coordinate on this disk, so if t is a formal coordinate, at x. For example, you can choose an ordinary coordinate and view it as a formal coordinate. Then O of dx is identified using this t with functions on the standard disk. And standard disk functions there are just formal power series in t. And then you can take O of dx times dx star, which is a punctured disk. And this is, so if we delete things from ordinary disk, we get Laurent series. But, well, there are conditions on convergence of them in the analytic world, and they could be infinite in both directions. For formal disks, in order, we should take formal Laurent series, but formal Laurent series do not form a ring in general if you consider them infinite in both directions. So you should take series which are finite in the negative direction. And that is a ring and moreover a field. So it's a field of functions of formal Laurent series. And well, the fact that this is intersection means that we should have inclusion of both of these rings inside K of t, inside this field. So this will be called capital K, and this will be called O. And so, of course, O is included in K. So this is, if you like, the ring of integers. So we have a non-Archimedean valuation, which is the order of this series at 0, and O is the set of series with non-negative valuation. And also, we can embed these functions on x minus x into K. And this is obtained by taking the Laurent expansion. So, of course, to take Laurent expansion and end up here, you need to choose a coordinate. But it's easy to show that if you think about them canonically as this, without choosing coordinate, then this inclusion doesn't depend on the choice of the coordinate. It's not on? It wasn't on. Ah, okay. So bundles E are defined by transition map G from one of these charts to the other. So let's say from the disk to x minus x. And so this is I can write it in terms of this coordinate. So this G of, it will lie in the group G, points over this field K. So it maps from this puncture disk to G is just this group of now it works. What? Works? Okay. Good. Why is it called loop group? Okay, well, you should think again about this puncture disk. So puncture disk is like an annulus. It's a disk, but from which you took out the middle. So, and we are looking at, for complex numbers, if you're working analytically, about holomorphic mappings of this disk into the group G. But now, of course, a holomorphic mapping like that is determined by its restriction to some circle, real circle, going around this point. Because Fourier expansion on the circle is the same as the Laurent expansion over this disk. And so this is really mappings of the circle into G in the analytic case with some analyticity properties, and that's why it's called the loop group. Other questions? Okay, so this is orbits, and we can generalize this. So we can, instead of removing one point, why should we remove just one point? We can remove any finite set of points. So suppose S in X is a finite subset, and then we can consider two charts. So first of all, affine curve X minus S. So I want the subset to be non-empty. So this is going to be an affine curve. And the second is a disjoint union over points in my set S of the disks D sub X. And I'm going to, for each of these points, I'm going to choose coordinates. Well, maybe I don't need to go into these details. Anyway, there are these two charts. So this is like U1, and this is U2. And then the intersection of these charts, U1 intersects with U2, will be the disjoint union of the punctured disks. And then, so you will get the following presentation. Bond G of X is going to be the quotient. So we need to take the group G of function, G-valued functions on this product, on this union, which is just the product over X in S of G of the disks dx star. On this side, we will take the product over X in S of G of dx. And on this side, we will have G of R. I can write it algebraically like that, or I can also write it geometrically. So I can write G of dx star, G of dx, and G of x minus x. And so here I can also write it this way, but there is a product here, and here is G of x minus x. So that's also a valid presentation for any finite subset S. But now this is for semi-simple groups, which have the property that we can trivialize any bundle by removing just one point. Remember that for G equals to C star, which is kind of the simplest example of reductive group, that's not the case. There is no set S that we can remove to trivialize all possible bundles. And so in that case, we need to consider we need to remove all points. Well, you might think that if you take a curve and remove from it all points, you get an empty set, but not in algebraic geometry. So in algebraic geometry, when you remove a finite set of points, this means that you allow your functions to have poles at those points. So if you remove all points, this means that you allow your functions to have poles anywhere, which means that you consider arbitrary meromorphic or rational functions. So this means that the ring R should be replaced, which is functions on x minus x, or x minus s, should be replaced just by the field of rational functions on your curve. So further generalization. is you can take a co-limit with respect to this set S. So take a union over all finite subsets S. And so that what you will get is the following presentation. So bond G of X will be the double quotient. So here is going to be a product over all points of your curve of G of dx. Here will be G of the field of functions. And here there is going to be a product over X and X of G of dx star. But here there will be a little technical detail, which is a prime over this product. So what does it mean, prime? It means that almost all factors. So what is a product? Product is a collection of elements of all these things. And product prime is a restricted product, which means that only finitely many of them actually have a pole, actually have negative coefficients. So product prime means that only finitely many coordinates are not in G of dx. So have a pole. So this condition comes from the fact that we're removing all points, but we're taking a limit from finite subsets. Okay, and so this this is over algebraically closed field. And if your field is not algebraically closed, so if K is not algebraically closed, question? This is field, yes. I don't quite understand the question. Yeah, well, this is of K. Of little k. So if K is not algebraically closed, then we should do the same thing, but we should but in this case we should take sets S inside of X of K bar, algebraic closure, which are Galois invariant. And so so then we will get bond G of X of K is going to be the product is going to be X of K bar modulo the Galois group and here it's going to be product, and here it's going to be G of K of X. And so if K is a finite field, for example, then this K of X, it was called a global field, which means that all completions of this field with respect to valuations are local fields, locally compact topological fields. And and this thing is actually a product over all valuations of this field K of x. So this field can be denoted by F. It's a global field. So what we get is the following double quotient. So here is going to be G of the product prime of evaluations of F of fields, local fields, FV. So if you have evaluation, so what evaluations on this field, K of x? They are, we can evaluate this field by taking order of a function at a point of x over some extension of K. These are all valuations. And so we take G over the product here, modulo G over the product over V in valuations of F of OV. And so this is a integer in FV. And then here we take G of F. So that's the presentation that we've got. And this is what goes under the name of arithmetic quotient. And the reason is that a similar quotient arises in number theory. So this is a global field of characteristic P, because K is a finite field. But there are also global field of characteristic 0. And those are just number fields, which are finite extensions of Q. And you can run the same story for them. So let me just comment on it, because it's not going to be very important, but at least for motivation, it will be. Thanks. So for motivation, it will be at least somewhat important. So definition, if F is a global field, then the ring of Adels AF is this product prime of F sub V, where V in valuations of F. So over fields of characteristic P, global fields of characteristic P, they all have this form. It is literally that. Over number fields, there are two kinds of valuations, which are Archimedean valuations, and which arise from embeddings of your field into real and complex numbers, and taking the usual absolute value. And also non-Archimedean valuations, which correspond to basically p-adic valuations. And prime means in this case that, so being an integer makes sense in non-Archimedean valuations. And so there should be finitely many instances like that. And then O F. So let us call it A. And OA is the product over V in valuation non-Archimedean of F or V. So rings of integers in non-Archimedean fields FV. And So in this case, all valuations are non-Archimedean, so you don't have to worry about it. And then you can define this arithmetic quotient M, which is your group G over A, modulo G over OA, and defined and modular G of F. And so this is a generalization. So if F equals to K of X, we get Bon G of X of K. So M is equal to this. Okay, and so example, which is not of this type, is, well, we should take a field of characteristic 0, so F equals Q. So in this case, the Archimedean valuations so all the primes, which correspond to embeddings of Q into p-adic field QP, and also infinity, which corresponds to the usual absolute value valuation, which corresponds to embeddings of Q. If you complete Q with respect to that valuation, you get real numbers. And so you get, so this A, in this case, is just R times the product over prime with a prime QP, which means that only finitely many of them fail to be in ZP. And OA is, well, here we don't have ring of integers because it's Archimedean. The other are not Archimedean. So that's the product over the primes P, ZP. And so we will get our quotient is going to be G of R times the product prime of G of QP, quotient G of ZP, and product prime in this case means that almost all elements are 1, because if this coordinate is in here, then we will get 1. And then this is going to be modulo G of Z. And, well, it is known that so G of Z is dense in this product, and therefore actually the product. So this whole group maps to the identity. So this is just a quotient of, I'm sorry, G of Q. And so so what this is well, there is some. This is non-trivial, but it's proved in number theory that this is the same. So the map from G of R into here is surjective, and so this is just G of R. So there is a G of R action on the right, and this is just G of R modulo G of Z. So this is a manifold which, for example, if G is SP2N, this arose in the, so we'll get SP2NR modulo SP2NZ. And if you also take quotient by unitary group, then as Sam explained in the previous lecture, this is the moduli of abelian variety of genus N. So this is the arithmetic quotients in number theory. And basically, well, Langland's program arose as an attempt to, prove some results in number theory, for which you need to. So another example, of course, classical example is G equals to SL2. And in this case, you get SL2. So this is a special case of genus 1. And so if you quotient by U1, well, this is the upper half plane. And so this is moduli of elliptic curves, or M1. So for me, this distinction is not going to matter. This is where modular forms live. So modular forms have important applications in number theory, and Langlands wanted to understand the modular forms and their higher rank generalizations, and for this purpose, one needs to work on this thing, and actually, but then you might as well work on this quotient for any global field, and in particular for global fields of positive characteristic, which are these, and in this case, it reduces to algebraic geometry, which is moduli of bundles. And this is very good because we know a lot more about algebraic geometry than we do about number theory. And actually, it also turns out that sometimes, I mean, for example, there was an important conjecture in this theory which Langlands couldn't prove, and it was unproved for 45 or 50 years, which was called fundamental lemma about this arithmetic situation. But it was proved by using this analogous situation in characteristic P using algebraic geometry. So this is just a little aside. Of course, we are not going to talk about any of this because it's very complicated and I'm not qualified to give a course about this. So, but what I want to say is that this presentation is already good for any reductive group, not necessarily semi-simple, because now we removed all the points. And of course, if we remove all the points and go to the field of functions, then any vector bundle or any G bundle will be trivialized. Because any bundle, as I explained, is Zariski locally trivial. So in particular, the Jacobian of X can be written as this complicated quotient for the case of G equals to GL1. And I invite you to think about, so if G equal to GL1, what you obtain is that Jacobian of X is, well, in which I pick a 0, so it's a group structure, is a multiplicative group of A, which means invertible elements here, modulo multiplicative group of the ring of integers, and modulo well, let's work over C, then it will be like that. And so this, you should think about this and discover that this is in fact the group of divisors on X. And this is the subgroup of principal divisors. Well, at least modulo scaling. So and so this is the presentation that Sam explained in his lecture. All right. So now I want to talk about, start talking about Hitchin system, which is the main thing I want to discuss. And for this purpose, well, Hitchin system is an integrable system. Integrable systems live on symplectic manifold. But we don't have a symplectic manifold yet. So we need to introduce one. And of course, the most common symplectic manifolds are cotangent bundles of ordinary manifolds. So we want to define cotangent bundle of bund G of X. But actually, of course, like I explained, bund G of X is not a manifold. not even a scheme. It is a certain very singular object. Well, it is a smooth stack, which is a quotient of a smooth, locally it's quotient of a smooth variety by a group, by an algebraic group. And for such things, you can define cotangent bundle, which is another stack. And there are cotangent spaces which you can define, which are actually complexes. But this is not what I want to do. I actually want to do down-to-earth theory of integrable systems and study usual symplectic manifolds. Well, luckily, what happens is that there is an open set. So I'm going to assume that the genus bigger or equal to 2. And I'm going to take, let's say G is going to be simple. And let's say adjoint, just to make things very simple. So which means there is no center. So in this case, well, I said that this was a stack. And the main feature of a stack compared to scheme is that points have automorphisms. Well, it turns out that in this situation, if you pick a generic bundle, it doesn't have automorphism. So automorphism group is trivial. And so generic and I will explain something about what this means, but generic bundles have trivial automorphism group. So this means that they correspond to a locus where in this presentation as a quotient of a variety by a group, the group is going to act freely. So stabilizers are trivial. And they form an algebraic variety, smooth algebraic variety. Bon G of X with a circle. So as long as we restrict to some open set, this stack, which is a functor of points, actually is representable by some variety. And I should explain what this generic means. So there are many, there are many ways to choose this open set. One nice way is to consider so-called stable bundles. So let's consider an example where G equals to, let's say, PGLN. So this means that G bundles are just rank n vector bundles. Modulo tensoring with line bundles. And for defining stable, it's not going to matter modulo line bundles because stability doesn't change when you tensor your bundle with a line bundle. So there is a notion of a slope of a vector bundle. So if E is a vector bundle on X, then we have two integers that we can attach to it. One is the degree, which is the first Chorn class. And the other, so this is called D of E. And the other is the rank, dimension of the fiber, which is denoted by R of E. And then we can define the slope, which is a rational number, so which is mu of E. And this is degree of E divided by the rank of E. And the definition says that E is stable if for every subbundle E prime inside E, which is strictly contained in E and not 0. Because for 0 bundle, we cannot define this ratio. But for every such subbundle, the slope of E prime is strictly less than the slope of E. So that's a very important definition. And there is a similar definition for other groups, but I will not give it. It's technical. And the precise meaning of this generic, one of the good ways to define this generic is to consider stable bundles. So the theorem is that stable bundles form a smooth variety which is an open subset of band G. PGLN bundles, yes. And they have trivial automorphisms. They have trivial automorphism. What? So what? I'm sorry. Yeah, no, but it's no, it is not. It's only defined modulo n, because when you tensor it with a line bundle, the degree changes by n times the degree of this line bundle. But if we choose a vector bundle, so it's an exercise. If L is a line bundle and E is a vector bundle, then E is stable if and only if E tensor L is stable. And this means that while this degree is not defined, the notion of stability is defined. Okay, so it's a subset of band G of X, where G equals to PGLN. And so generic, so this means the generic bundle is stable. And has no non-trivial automorphisms. And so this set band G circ of X will denote the moduli of stable bundles. So which is a smooth variety. And so one can consider, therefore, MG circle, which is the cotangent bundle of band G circle of X. And so Hitchin system will initially live on this cotangent bundle, but actually it turns out that there is a partial compactification of this, which is also a symplectic variety, and the Hitchin system naturally lives on this compactification. This is actually a very common phenomenon in integrable system, that, you know, if you with pedestrian approach to integrable system, when you write formulas, normally you define it on a certain rather simple variety, you know, a affine space, or maybe some open subset of affine space when some coordinates are not equal to each other. But then many integrable systems naturally extend to certain compactifications of the original variety on which you define them. And this is a kind of deep geometric fact. So they know about geometry. That's a very important feature of integrable systems. And this is not an exception. This happens here as well. So there is a compactification of this space, partial compactification, which is called the Hitchin moduli space. And the system will extend to that space. But before we do anything, we really should ask ourselves, okay, we have a variety, but variety has a dimension. So what is the dimension? And for this purpose, we need to compute the tangent or cotangent space, because, of course, dimension of the variety is equal to the dimension of the tangent or cotangent space to this variety at a point. So what is the tangent space at a bundle E of this bun G circle of X? Well, this is a very standard thing. So tangent vector means that we are going to move. So this is our moduli space of bundles. And there is some bundle E. And then we look at tangent vectors. So what does it mean? Tangent vectors means that we kind of can move in that direction and deform our bundle. So this is deformations. This is just the deformation space of this bundle E. And it's easy to see that this deformation space, so it's an exercise. The deformations of the bundle E are classified by H1 of X with coefficients in adjoint bundle. So what is adjoint bundle? So I told you that for every representation of your group G, if you have a G bundle, you can define the vector bundle associated to this representation and to your bundle. And in particular, you can take the adjoint representation. And that will be the adjoint bundle. So here is an example what happened for GLN. For any G, actually, it doesn't matter, and it doesn't matter that it is stable. So, but if it's not stable, then this will kind of classify first order deformations, and then it may not extend. So, but the calculation is the same, and so so here is an example. So let's take G equals to GLN. This is not semi-simple, but never mind. Well, maybe PGLN, okay. So, so in this case, well, okay, so let's take GLN. So in this case, it's vector bundles. And so in this case, deformations of E is like deformations of projective modules over the sheaf of functions on X of rank n. And deformations over modules over any ring are classified by X1 from the module to itself. Because what does it mean, deformation? Deformation means that you define some module over the ring of dual numbers, k of h over h squared, which modulo h gives you a module. But this module, if you consider this, and it is free as a k of h over h squared module. So if you view it as a module over k, it's an extension of E by itself. So this is how deformations work. And so deformations of E is just going to be x1 of EE, which is the same thing as x1. So we can move E to the other side, will be E star. So from the trivial bundle, from O, to E star tensor E. And this is exactly the adjoint of E because E is a GLN bundle. And this is the same as H1 of X with coefficients in adjoint of E. But this calculation is easy to generalize to any group. Huh? I cannot hear. Can you speak up? Okay, so if you have rho is a representation of G to GLN, and E is a G bundle, then we can define E sub rho. This is corresponding GLN bundle, which is associated. So the transition function G goes to rho of G. And in particular, we can take rho is the adjoint representation. So action of the group G on its Lie algebra. Okay. All right, and so this classifies deformation. And so we get that the tangent space is equal to this H1. And this means that the cotangent space at E of 1 G of X circle is the dual of this space. So it's H1 of X with coefficients in adjoint representation, adjoint bundle of E dual. But then we have Serre duality. Which says that this is the same as H0 of X with coefficients in the dual bundle. Tensored with the canonical bundle, which is a bundle of one forms on X. But this is the same. Of course, there is a trace form on the Lie algebra, the killing form, and therefore the adjoint bundle has also an invariant inner product, so it is self-dual. And so what we get is that this is equal to H0 of X. So I think it is customary to write Kx as a first factor, tensor product with the adjoint E. And so what is this? This has a very vivid geometric interpretation. So these are one forms on X, holomorphic one forms on X with coefficients in the adjoint bundle. So as objects on X, they are one forms, but they valued also in the adjoint bundle. And such objects have a name, because they appeared in physics in the work of Higgs, and so they are called Higgs fields. So this is the space of Higgs fields for this bundle. And so now I'm ready to define the Hitchin integrable system. So for this purpose, I first need to recall something about Lie algebras. Because adjoint of E is valued in the adjoint representation, which is the Lie algebra G. So recollection about Lie algebras. So, yes. Oh, I'm sorry. Yeah. I was going to say what dimension is. Okay, thank you. So what is the dimension of this H1 of X with coefficients in Kx, tensor product with endomorphisms of E? H0, I'm sorry. Well, for generic bundle, so first of all, we have the Euler characteristic of which is the dimension of H0 minus dimension of H1. And as always in geometry, Euler characteristic is a very robust thing. It does not change under deformations. So this is deformation invariant. And but for generic bundles, so this is 0 for generic bundles. So it requires some, arguments, but one can show this. And this is logical because, well, this thing is invariant. So if you take generic bundles, if you take a non-generic one, this thing will be positive, and this thing will be bigger. So that's what happens when you have singularities. Your tangent space at a singularity actually is bigger than the tangent space for generic point. So really, it's equal to the dimension of H0. And so you need to compute the Euler characteristic. But Euler characteristic can be computed. So let's say we have, so the Euler characteristic, well, if your group is adjoint, then you have to be a little bit more careful because you have several connected components of bund G. But if the group is simply connected, then, well, you can compute chi for trivial bundle because it's deformation invariant. And for trivial bundle, so then it is dimension of H0 of X with coefficients in Kx times the dimension of G, because this is just a copy of G in that, adjoint E. So this is just a copy of G. And so this is the space of one forms. Well, for the trivial bundle, so you need to compute dimension of H0 minus dimension of H1. But this is G, because this is the space of one forms, holomorphic differentials on your Riemann surface. And this is, by Serre duality, it is H0 of X, Kx inverse times Kx, so just O dual. And this is just one dimensional. So you get 1. And so G times dim G minus dim G, so this is G minus 1 times the dimension of G. And so this is the answer for the dimension of this for semi-simple groups. Huh? Trivial bundle is not generic, but the Euler characteristic is the same as for generic. Okay, so now if you have a reductive group, yes. Yes, so what I'm saying is, first of all, they have a notion of Euler characteristic. Euler characteristic is a topological invariant, so it does not change when we deform the bundle. In particular, it's going to be the same for all bundles, even for non-generic ones. On the other hand, for generic bundles, this H1 is going to be 0, and H0 is going to be the smallest possible. So for generic bundles, Euler characteristic coincides with dimension of H0. And so then we compute the Euler characteristic in the simple case for the trivial bundle and get this number. And I should say that so if G equals to C star, then Bon G of X is just, so if you forget about the automorphism groups, it is just the Jacobian of X, which has dimension G. And so this means that, so here is G times the dimension of the group. And so this means that if your group is mixed, it's a mixture of a semi-simple and abelian, so any reductive group. So G general reductive group. So we get dimension of Bon equals to G minus 1 times the dimension of the Lie algebra plus dimension of the center of this Lie algebra. So because for each commutative component, we get an extra unit. We have G instead of G minus 1. And so in particular, in example, if G equals to general linear group, which is, yes? Yes. No. This is already, G minus 1 is already taken into account here. Okay, so if G equals to GLN, what we will get is G minus 1 times n squared plus 1. So that will be the dimension. Okay, so now I use that, there is no, if G is not semi-simple, then generic bundles have automorphisms, and so this will never be 0, actually. So like, let's consider that case. So if G is C star, then this is just a one-dimensional space, and so you're just computing the Euler characteristic of the canonical bundle, which is, so if you compute Euler characteristic, this is going to be G, and this is going to be 1. So if you compute the difference, it is G minus 1. But if you think about Jacobian just as a variety without considering the automorphisms, it is G dimensional. Yes? Yeah, you can write it like this. G minus 1, this is what Kohler was suggesting, dimension of G semi-simple plus G times dimension of the center. Huh? But this is also correct. All right, so, and so now let me just give I finished by giving definition of the Hitchin integrable system, and then we will, discuss integrability, prove it, compute examples next time. So Hitchin integrable system on T star of Bon G of X circle. So what is an integrable system? This is just a collection of Poisson commuting functions whose number is equal to the dimension, half the dimension of your symplectic manifold. So in this case, the dimension of this base. and which are functionally independent. And so what? In other words, you can think of it as if you make these functions into a vector. This means it's a map to it's a map to a vector space of dimension equal to the dimension of this thing, which is a Lagrangian fibration. Which, being Lagrangian fibration, at least generically, is equivalent to these functions being functionally independent and in involution. So they Poisson commute. So for this purpose, so let me do it in the case of GLN, or maybe SLN. So in this case, the dimension of Bonn is equal to n squared minus 1 times g minus 1. And in this case, so what is this thing? This is a set of pairs, E phi, where E is a stable bundle, and phi is a Higgs field. So phi is a one form on X with coefficients in endomorphisms of phi 0, which means it is trace 0 part. So this is for SLN or for PGLN. It doesn't really matter in this case. And so we define, so Hitchin map is P from cotangent bundle of Bonn G of X circle. And this maps into the following space. It is a direct sum from I equals 2, from I equals 1 to n minus 1, H0 of Kx, of X, with coefficients in Kx to the power I plus 1. Now, by the Riemann-Roch theorem, this has dimension equal to 2i plus 1 times g minus 1. And so this whole thing has dimension, the sum of these things. So this has dimension, sum of 2i plus 1 is n squared minus 1. So we get n squared minus 1, g minus 1. That's exactly what we need. It's the same as the dimension of this thing. And this space is called the Hitchin base. So usually denoted Hitch. So it's a vector space. And the map is given by the following. P of E phi is equal to the trace of phi squared, trace of phi cubed, up to trace of phi to the n. Trace of phi to the n. So, so note that since phi is a one form, then trace of phi squared is a quadratic differential. Trace of phi cubed is a cubic differential, and so on. So that's exactly a map of this form. And the theorem of Hitchin is that this is an integrable system. So coordinates are Poisson commutative and functionally independent. It's a very large class of systems because it's attached to any curve. Yes? Well, the role is that we're taking, well, of course, it also makes sense for complex geometry. So it can be complex differential geometry. But the role is that we're taking H0. So these are global objects. They are global quadratic differentials. And we're using Riemann-Roch theorem to show that the dimension is this. Yeah, absolutely. And Hitchin wrote his paper in the setting of complex differential geometry. But again, as I explained, that because of the Gaga theorem, there is it is equivalent to work on complex differential geometry or in algebraic geometry over any field of characteristic 0. And in fact, but this makes sense in algebraic geometry, so you can even do it over fields of characteristic P. Can be done over other fields, yes. And so, I will stop here, and then next time we are going to prove this theorem. We will generalize it to other groups, and then we will consider generalization to bundles. So this is a bit complicated because we have to consider curves of genus greater than 1, though they're rather complicated, not so convenient to compute with. But we will consider bundles with parabolic structures, which is a kind of more general case, so-called ramified case. And this will allow us to consider bundles on P1. So P1 doesn't satisfy our assumption. It doesn't have stable bundles. But if you add parabolic structures, it will have stable bundles. And we will be able to work on spaces which are much more easy to work with by hand. And in particular, we will consider the case of GL2 with parabolic structure. And we will show that in this case, we obtain a famous integrable, well-known integrable system, which is called the Garnier system. And so we will actually calculate the Hamiltonians in coordinates. Thank you.
Let's thank Pavel. Are there any additional questions? So the question is, what's the definition of coordinates on the cotangent bundle?
So we don't need coordinates. There is a canonical symplectic structure on cotangent bundle for the manifold on variety also. And so this is, to formulate this theorem, we do not need coordinates. That's actually a very... Hitchin base is a vector space. So if you choose a basis, you will have coordinates. And those are algebraically independent. These are integrals. These are going to be first integrals of the Hitchin system. Hitchin system does not have a distinguished Hamiltonian. You can take any of the coordinates and use it. So there is, we really should think about all flows for all of the integrals. Yes.
So the question was, what's the definition of generic bundle?
Yeah. So generic for me will be stable bundle. For semi-simple groups, it will be, well, actually, even for reductive groups, the definition will be stable bundles. They don't always exist. Like for P1, for example, there is no stable bundles. But for P1 with parabolic structures, we will introduce the notion of stability, and there will be stable bundles. They will satisfy the same property, and we will obtain interesting integrable systems in the same way. So the point is that if you don't have stable bundles because you have too many automorphisms, so in this situation, you want to rigidify your problem, which means to fix, for example, you can fix elements in fibers at several points. And this will make a lot of bundles which were not stable into stable bundles. And then you can do this, play this game, and you will get lots and lots of interesting integrable systems. You will even get more interesting ones if you also fix derivatives, not just points, but also derivatives and second derivatives at those points. So that's called wild ramification. And this will give you really interesting things. For example, you can get Toda, affine Toda systems this way for any group, and many others.
Okay.
No, you will, okay, same change of stability condition. So there are various definitions of stability, which may differ. For example, for parabolic structures, you can fix so-called weights, and there will be different stability conditions. But generic bundles are going to be stable with respect to any condition, basically. And this, what you will get doesn't depend too much on these conditions. I mean, what depends on these conditions is what kind of open set you will take. So you know, you take some opens, like which points you are going to include. And that's not so important as long as we know what happens on the generic locus.
Other questions? No. I'm sorry, we cannot hear you from there.
When take trace, what? Trace of phi is 0, right? But trace of phi squared is not 0. I cannot hear. I'm sorry.
Yeah. Okay. So I'm sorry. We would have a mic at the end of the room next time, but it's just impossible to hear. Question?
It's this takes more than 2 minutes to explain. So.
Okay. Maybe one more question and lunch. Comment.
So he was asking the square of the one. So he was asking the square of a one form should be 0 on the curve.
The square of a one form? No, we don't know. It's not. It's not exterior square. It's a tensor. So kx is a line bundle, and so when we take like sections is something times dx, then sections of square is not dx wedge dx, which is indeed 0, but dx tensor dx. So we have a tensor powers instead of wedge powers. Ah, yes. Okay.
All right. I suggest the remaining questions can be moved into discussion sections. And let's thank Pavel again and have a lunch break.